third.
Okay.
All right.
Okay. So I have a question about the second problem. I just want to make sure, is that something we should be doing on Excel? Like we're doing it technically, I guess, like by hand, basically using it in Excel. Okay.
But that's how I did it. I mean,
Okay, yeah, I saw it
could be done with, you could do the same thing with MATLAB. I kind of don't want people to just plug it into MATLAB.
Yeah. So that's
Right.
I figured that's right. I just wanted to make sure that I was doing that right. Okay.
Yeah.
Right. So I did that in Excel. And then for the third one, I got like as far as how we broke it up, like kind of the example in class. And I think what's confusing me is when I'm trying to figure out, I guess, what is that? I think it's the correlation for n. So when you break it up, you're kind of left with like the rxx tau, and then the two parts that you can like set to 0 because it's independent, but it wouldn't be 0 because you have the constant there, right?
Well, so if they're independent, you can break up the expected value of the product into the product of expected values.
Mm-hmm.
Okay.
Yeah.
But where you go from there depends on what the product of the expected values is.
Yeah, because n of t is like m of t, which is the one that has the mean of 0, but it's also plus b. So I figured you can't set that. That wouldn't be 0. It would have to be b.
Right. The expected value of n is b, right?
Okay.
Because
Yeah.
it's that would give you the expected value of a sum of a thing that's 0 mean plus a constant b. Yes.
Okay. So I got that, and then what's messing me up is when you get to the very last part, it's the expected value of nt times nt plus tau, which then it would be, I think RNN, that's the correlation. Pretty sure, right? Yeah.
Right.
Give you the correlation, which if you just broke that up again, it would just be the expected value of n of t times the n of t plus tau, which I think is what's confusing. I don't know.
Well, so, okay. So you can't break that up. That's the thing you can't do because n is not independent of itself even at different times.
Yeah.
Okay.
Yeah.
And even though it's white noise and it seems, oh, if they're different times, then maybe they are, but you also have to account for the same time, where tau is equal to 0. And so that's not 0, right?
Yeah.
So you can't break that up. And so it does, that quantity is RNN by definition.
Yeah. And then you would like use the equation to solve for RNN like tau, right? So it would be the expected value of n of t times the n of t plus tau. You multiply it. And then, but when you try like, how we would separate it to solve, like I think that's what's confusing me because it's like I'm in like a loop of just having like
you just got to go one more step deeper, right? Because then you're going to have RMM as an element of that, right?
Yeah. Okay.
And you know some stuff about that.
But RMM, is that what we just so that's just the variance, which is the s squared?
Not exactly. Okay.
Yeah.
So RMM is going to be based on what we know about m,
which is a mean of 0
and white noise. So that means a little more about what RMM should be from the fact that it's white noise.
I think I get it now.
Okay.
All right. Okay.
You can review that part of the slides from the last class if you need to, where we talked about white noise.
What I was missing for sure. Okay. And then I guess then I just want to clarify for like the MATLAB ones where it says reducing the lag. Does that mean we're basically, you want us to like focus on like a more, I guess, reduce the x-axis to where like to cut it off where it stops repeating? Like I can show you like the ones that I got.
Here, let me see what I can. I think I have to enable you. Okay, you should be able to share now.
Okay. So this is what I kind of got for I put it all in a Word document to help me see better all the things together. But this is when I did like the regular signal of time versus signal, and then when I did the covariance. So we should, because it's kind of like hard to tell. I guess, I mean, you can tell like stuff from the thing, but it would be easier to cut it off like here.
Yeah, I so I generally, would say, at some point where you see, well, in some ways I want to say, okay, where it kind of first kind of significantly crosses zero, but that's not always a good rule because sometimes you have, I mean, if you look at the next one, right, you have a kind of an oscillating pattern.
Yeah.
Right. And so you don't want to say, well, just go to the first zero cutoff. If you see a pattern, you want to go to where that, where you see that kind of decrease, the amplitude of that thing kind of decreasing there, plus or minus 100 or so, So I kind of agree with where you're saying, well, we'll just really consider it within, where you see that kind of that central feature kind of drop off.
Okay.
Right. I kind of, I agree with that.
Just to make it easier to like.
Yeah.
Okay. I just wanted to make sure that I was understanding that correctly.
Yeah. No, I think you have the right idea there. And,
Mm-hmm.
again, it's a bit of a judgment call. So there's not necessarily a perfect way to do it.
All right. Okay. That makes sense. I haven't started the last one yet, but I think I should be okay. Yeah, I think those are like my only questions that I had.
All right. Very good.
I appreciate the help.
Okay.
Number 3 was throwing me for a loop.
Well, I mean, these aren't easy. They aren't supposed to be easy.
No.
They are supposed to, I'm really trying to get people to think about these things and think about what they mean.
Yeah, for sure. I feel like I was making it too complicated because I literally just kept going back and forth, going between like the things. Yeah.
It seems like you're trying to think it through and make it make sense, which is what I really want people to do. Okay. Okay. Great.
All right. I appreciate it. Thank you so much.
Sure.
I just had a couple quick questions.
Sure.
So first of all, for number 3, are we supposed to assume that it is stationary as well?
Ah, great question. Yes. I should have said that, right? Yes. And I mean, that's sort of implied by the fact that, for example, the autocorrelation is given only in terms of one parameter. If it wasn't stationary, I'd have to have 2 arguments to RXX.
Okay.
But, that's not immediately obvious to people. So it's implied there, but it isn't stated explicitly, and you are correct.
So when you say there's, just so I have understanding, so when you have, it says restricted to 2 arguments, it's like 2 variables? Because
it would have to have 2 time variables if it was non-stationary.
Okay. Just 2, there wouldn't be more?
Well, so, tau represents how far apart 2 time points are.
Yeah.
But if it's not stationary, we have to actually pick 2 specific time points.
Okay.
So like T1, T2,
Mhm.
and characterize it for all of the combinations of different time points in the signal.
Okay.
Yeah, so that's why this is much simpler.
Okay. For that same question,
Mm-hmm.
because it was a white noise, MFT's white noise random process, I got a delta function involved in my answer. Is there, like, there's no way I can simplify that down further, is there? No.
Well, how much simpler does it get than a delta function?
Okay.
But you're right, again, the autocorrelation of white noise is a delta function.
Right. Okay. Oh, for number 2, the one right above that,
Mm-hmm.
did you want us to do like present it graphically like we did in class?
You could do that, or you could just do it in a spreadsheet, which I
Okay.
had on one example, or
Oh, that's right.
something like that. I just don't really want people to just plug it into MATLAB,
Okay.
because its answer probably won't agree with mine.
Okay. So
Yeah.
a spreadsheet's good though?
Yeah, sure. That's
Okay.
fine.
That's good.
That's the way I did it, really.
Okay.
Yeah,
I was about to write it all out and I wasn't thinking of spreadsheet, so
yeah, I can.
easier.
Sometimes people write it out and do it literally by hand, and it's like, why did
Yeah.
Sometimes
That's why
people do that.
I was looking at a problem. I was like, I think I'm gonna wait to do that one because I don't really want to write it out unless I have to.
No, in general, I'm in favor of using computers.
Okay, that's good to know. I don't know if you can answer this because this is like kind of a specific question, but for number 4, since wouldn't that just be one frequency because it's a sine function? And
it's a sinc function.
Okay.
Which is not the same as a sine function. So remember, a sinc function is a sinusoid, but it decays as you get away from 0.
Yeah. I looked that up in the Fourier transform table because it wasn't in the document, and it's a rectangular function. I'm not exactly sure, like, I've never like seen a rectangular function before. Or I think we've seen it, just not by that name. Kind of like we're doing like step functions, and like you have t minus 1, you add that, and then you subtract u of t minus 3 or something, and you get that rectangular shape.
Yeah, that's a way of writing a rectangular function.
Okay.
Sometimes it's called a box function or a boxcar function. There's a lot of different names for it.
Okay.
But yeah.
Okay. When I was looking that up in the table, I think I understood it. Let's see if I can find. I just had it in Google Images. I'm just trying to find the table I was looking at. So the one I was looking at used F. I assume that's just a frequency component, but in hertz instead of
Yeah, and I will say it's not very important, to have the precise transform.
Okay. Just that we know it's a rectangular function.
Yeah, just have because that's what's important here. You know, how those two things kind of relate to each other.
Do we still try to solve for it mathematically?
I mean, so first of all, I mean, you can find it in a table, right?
Mm-hmm.
The sinc function is one of those that I listed that you should be pretty familiar with, right? Sinc function, rectangular function.
Oh,
You should
yeah.
be familiar with that.
Okay.
The exact relationship, you know, in this case, it's not important. That's not to say in some other situation it might be important to have the exact mathematical form of it. Although on an exam, I would actually give you a brief table that would include the exact mathematical form that I would use.
Okay.
Okay. But yeah, and you can find them in different forms, and so that I know that can be kind of confusing. But basically, you know, they're all going to give you that a sinc function is some kind of rectangular function.
Okay. Yeah. Now that you say that, I remember that exercise. I think it was one of the first classes where you had the Fourier or the function in the Fourier transform. I remember that being one of them. Okay. And then, okay, and then I had one last question. I think this may have to do with my understanding of how MATLAB computes the autocovariance, but it was for number 6. So you asked us to calculate it from the Fourier transform and then also the autocovariance. And they have my graph, they have very similar shapes. Because that was like one of the things that we did in class that they should be expected. So that makes sense to me.
Right.
But they also, the autocovariance has twice as many data points.
Ooh. Why do you think that is?
That's here. Give me a second to think.
That is a thing to think about on that one.
All right, I need to spend a second thinking about it.
Yeah, it's fine. Nobody else is here. So when you computed the autocovariance, right, it gave you something that was twice as long as the original.
Yeah.
Yeah.
I'm trying to think. I'm looking back at my notes about autocovariance to see if that's what intuitively should happen.
Well, I mean, if you look at that plot, you see it's symmetric, so there's redundant information.
Yeah.
Right.
Yeah. It's redundant information, but it's like a shift of the function is almost what it like visually what it looks like, or not shift, but it's like divided by all the data points divided by 2.
Yeah. So that's just because of the behavior of that XCOV function.
And the MATLAB XCOV function.
Yeah. That's by default it gives you the positive and negative sides of the lag. Which it should, because that's, that's normally how we plot those things, even though it is kind of redundant. But, it basically doubles your signal in terms of the length of it by doing that. So
Right.
you can control that, with options in the XCOV if you want to.
Okay. Doesn't the Fourier transform also show redundancy as well?
Yeah, but it always does, right? Yeah.
So one of those redundancies match up though?
Actually not. And the reason is, you're going into that different world of the Fourier. Right? So if something is redundant in one world, it's not, that doesn't lead to redundancy in the other.
Okay.
Okay. Redundancy leads to, symmetry of that kind leads to real valuedness in the other world.
Wait, okay. Can you repeat that one more time?
Yeah. So if something is all real in the time domain, it is symmetric in the Fourier domain.
Okay, yeah.
Okay, and that's why we get that, what we call redundancy is symmetry, actually, right? And it works the other way, right? If something is symmetric in the time domain, it gives us something that's all real
The Fourier domain.
in the Fourier domain.
Okay.
Which it should, because we should be getting a power spectrum, which should be all real, by the way. So that is not really the issue with that, thing being twice as long. But it's twice as long because there's redundant data in it. In other words, if your original signal was 512 time units long,
yes.
Okay, XCOV just by default is going to give us something that's 1024 long or so, but everything's redundant, so it still only has 512 unique pieces of information in it. So in other words, we haven't produced any new information. Okay.
Yeah.
It's just that's what XCOV does. Now you can limit. There's a option in XCOV called max lags that tells you you can limit the maximum number of lags that it uses to a smaller number, but it's still going to give you the positive negative symmetry.
Okay. I think I'm trying to understand that. So because with the lags, it'll go from 1 all the way to the however many 1 minus the data points in the signal, or data points minus 1.
Yeah.
Okay, so you would just be kind of chopping off that matrix. I'm still okay. So I'm still Can I share my graph really quick?
Yeah, sure. Hang on a second.
Okay. I'm still struggling to understand. Just one bit.
Okay, you should be able to share now.
So, like we said, we're talking about with redundancies. So I guess I understand the first part where you're saying it's gonna have twice the amount of data points, but wait, actually, let me think. Let me collect my thoughts before I continue. Okay, I get. Okay, so yeah, I understand that part, but the part in class where we said the expected value of the power function should equal the Fourier transform of the covariance, but obviously looking at this graph, that's like I can tell, you can kind of tell there is a relationship there, but it's shifted, like you said. So I'm having a hard time understanding where the disconnect is.
Well, there is a disconnect.
That's what we're supposed to figure out.
Zoom your graph out if you can. This new thing in MATLAB where you kind of interactively mess with the graph is a little weird to me, but okay, that's fine. That's fine. One of your transforms is twice as long, right?
Oh, well, so yeah, one of these is from a transform. Oh, one of them is a transform from the autocovariance, and one of them is the normal transform. Yeah, so yes.
That might have something to do with it. Are you comparing apples to apples?
No. So would I like adjust one of them to? Would I take like every other point of the covariance? That doesn't seem.
Well, okay, but the question, really the question is, so you've plotted that and labeled it cycles per recording period.
Yeah, my x-axis isn't the same for each because it's array index.
Yeah.
Okay, so
array indices may mean different things in the two cases.
Right. Okay.
So think about that.
Okay. So these ones should be, this should just be frequencies. That's right, because that's the one from the power squared. And this one is a Fourier transform of the lag, which would be, how would the units of the Fourier transform of like the autocovariance?
Well, it's still, so, well, remember how we calculate, so, okay. You have two different signals. You have two different signals of different lengths.
Okay.
Okay. I mean, the autocovariance is a signal with the same, essentially sampling rate or sampling interval between time points, but it has more time points.
Yeah.
Okay. Now, the question then is, how do we relate the MATLAB index to actual frequency? Because what you want to be doing is comparing these both on the same scale of actual frequency rather than their MATLAB indices.
Yes.
Okay. So if those two signals were the same in every way, same time interval between samples, same number of samples, then their frequency scales would be the same,
Mm-hmm.
just automatically. But that's not true here.
Okay.
Okay. So that's the thing you have to consider.
Okay. So obviously, like it's gonna be the frequency is gonna be twice as much. The time interval is gonna be there's twice as many data points. But where does that come in from? Or I mean, I don't know if you can answer that or not. That's something I just have to like figure out.
You are very close, and I'm going to let you work on that one.
Okay. Well, I'll work on that. Thanks for your help.
Yep, sure.
I think those are all the questions I had. So,
Okay. All right.
see you on Tuesday.
You Tuesday.